So now that we've talked about the logic of null hypothesis significance testing, I want to talk about one of the simplest forms of statistics. And when I say simple, I'm not necessarily saying that it's highly simple to understand if you've never been exposed to, statistical training and hand calculations and stuff like that. That's not my intention, but it is one of the simplest to sort of wrap people's head around at the onset, which is what are called Z-statistics or Z-tests. Now, this is different from a Z-score. So in some of my other videos in your scientific class, you might have learned about a Z-score. A Z-statistic is different. It's actually a very similar calculation for a Z-statistic or a Z-test. It follows a very similar type of calculation, but the difference is that this is actually used to compare two means to one another. And it's used with a single sample. So this is a single sample type of study or a single group. And what you are doing is you are comparing your sample mean, which is often notated by X bar or a capital M. So this is not me saying X bar divided by M. It's just that's the notation, is that people oftentimes will notate a sample mean with either X bar or M. And we compare this to a known criteria or a population value of mu. And so the null hypothesis states that X bar, or the sample mean, is going to be equal to mu, which is the population parameter. Now you might ask, like, what's an example of a study like this? Well, let's say that I own a car sales shop, and the historical average sales is equal to, let's just give it a round number of $1 million per month. Maybe our car shop does $1 million in sales every month. And I implement a new training procedure for my sales folks. Maybe there's a new persuasion tactic. And I think maybe this is going to actually improve sales in my auto shop. And so my alternative hypothesis states that X bar is going to be greater than mu because I am implementing this new procedure, and then I'm going to see how many sales we do in the next month. And we're going to compare that to this existing value. So existing is going to be mu, is the sales per month. And then maybe this new month, maybe we did $1,120,000 in sales. And this is like an average per employee situation. So let's say that I had 30 employees, and the standard deviation. So this is the average across those 30 employees with a standard deviation of, let's just make it another round number, of $100,000. So what we are asking is this significantly greater than this? Did my new procedure or my new sales tactic actually improve sales that month? And the reality is that every month is going to be slightly different, right? There's almost never going to be an exact, it's not, if your historical average is $1 million, you're not going to do $1 million every single month. What we are asking is, do we have evidence against the real population value, like against that, like, do we actually have evidence that this is differing significantly, or is it just random variability in sales? So in order to do this, we calculate what is called a Z-statistic. A Z-statistic. And what this does is, on the top part of all test statistics that are out there is the effect. And the effect is the difference between your sample mean and the population mean of mu. So this is asking what's the difference between them, but we can't just look at the difference because of course they're going to differ at least a little bit. And the difference here is going to be $120,000, but we're going to do X bar minus mu. divided by your standard deviation, divided by the square root of n, which is the square root of your sample size. So this is your sample mean. This is your population mean. This is your standard deviation, and this is your sample size. So all we have to do then is plug in the numbers and solve for z. But before we solve for z, we need to decide how are we going to determine whether this is a statistically significant increase in sales. So what we need to do is, just like I kind of crafted in that prior video where we talked about the logic of null hypothesis significance testing. Well, this is also, if we rewrite the null hypothesis, this is also like saying x bar minus mu is equal to 0, right? If you subtract them, there is no difference, because if they are equal to one another, the difference between them is 0, whereas this one is saying x bar minus mu is greater than 0. Okay, so the null hypothesis, HO, states that the difference is 0. Now, if the real population difference is 0, are we going to find 0 every single time? I asked this in the previous study, and really what I'm asking is my sample perfect? The answer is no. So even if the real population value is 0, we're not going to find 0 every single time. Sometimes we might find a difference of 5,000, sometimes a difference of 15,000, sometimes we might find a difference of 50,000, but we're asking, do we have evidence against the real population value being 0? Well, once we get far enough out here, it starts to look like it might have come from a different distribution. And actually, I'll draw this using a different color here. Once we get far enough out here, it starts to look like maybe this came from a different distribution. Now, these distributions do overlap, at least some, and that's where error can happen. Is that sometimes a value here, we might decide that it probably came from the orange distribution, but actually it came from the blue distribution. That's when we make type 1 or type 2 errors. But what's happening is that once we get far enough away from 0, remember, and I'm actually going to do this again here. I do this every single time. Remember, on my hand in that previous video, I wrote test statistic, and on my other hand, I wrote p-value. As your test statistic gets further away from 0, meaning as my Z-statistic gets further away from 0, my p-value decreases. And we're asking, at what point of your test statistic does your p-value become less than 0? That's when you, or less than 0.05, excuse me. That's when you would say that there's a significant effect. So, let's actually undo a few things here. Let's undo and just leave that null hypothesis distribution up there. What we want is, in any study, we set something called alpha equal to 0.05. And alpha is what we compare our p-value to. Remember that phrase, p is less than 0.05, that you've heard for years and years and years? That 0.05 that we're, or like that p-value that we are comparing this to, this is something called alpha. And what alpha is the maximum allowable type 1 error rate. We don't like type 1 errors. I talked about this in the prior video. We do not like type 1 errors, and if the null hypothesis is actually true, meaning that there is no difference between these two, we don't want to say that there is a significant difference when there isn't. But we are willing as a field to make a type 1 error 5% of the time that the null hypothesis is true. So if the null hypothesis is true, 5% of the time you're going to make a type 1 error. Well, we need to think about that. Remember, if we draw in these alternative distributions on either side, I'm just going to draw them in for just a second to visualize. Once we get far enough out here, we start to say probably it's more likely that it came from this distribution than this distribution, and we're going to say probably there's a significant effect going on there. So let's actually draw in where we would reject the null. This is called a critical value. And we actually have a critical value on both sides. And we start to ask ourselves, what portion of this distribution is in this shaded region? Well, 5% of the time that the null hypothesis is true, we're going to make a type 1 error, meaning that we're going to find a test statistic further out than the critical value here, and we're going to make a type 1 error in either direction. So what we do to determine, because basically what we have to ask is what is the value of z at each of these critical values? Because if we find a z that is further out than those critical values, we would say, yes, it's statistically significant, or that we have evidence against the null hypothesis. Well, if our alpha level is set to 0.05, we can divide that in half, and we know that out here in this shaded region is 2.5% of that total distribution. And there's 2.5% over here in this shaded region of the distribution. And so now the way that we need to lay this out is we need to put the 0th percentile way over here and the 100th percentile way over here. If you remember back when I talked about z-scores, it functions in much the same way as that. It's that eventually you get so far away from 0 that no test statistics are going to be any further out than that. That's the 0th percentile right here. And eventually you get so far away from 0 on the right side of the distribution that no test statistics are going to be larger than that. That's the 100th percentile. Well, between 0 and this line right here is 2.5% of the data. And so this line corresponds to a z that is at the 2.5th percentile. And this line over here on the right side corresponds to a z that is at the 97.5th percentile. And actually, I'm going to erase quite a bit of these markings here just to make this a little bit easier to read now. Let's keep going. Let's take this back to basics here. Okay. So we know that these are critical values, these little lines that I've drawn in, and we know that 5% of the distribution is in the shaded region combined. That means 2.5% is over here and 2.5% is over here. And so that means between 0 and this line is exactly at the 2.5th percentile because 2.5% of the distribution is over there, and then the 100th percentile is over here, and between this and this line is 2.5% of that distribution, and so this means that that line is exactly at the 97.5th percentile. So what we then ask ourselves is, what is the value for z at each of these levels? And that's going to give us our critical value, which is going to help us to decide, do I reject or fail to reject the null hypothesis? Well, we actually use the exact same z table that we used last time when we were calculating our z scores. Except this time, rather than going from z to percentage, we need to work backwards. We need to start with the percentage, which in this case, again, is the 2.5th percentile, and I actually need to move the decimal twice because a z table shows proportions, not percentages. So we're going to move this z value 2 decimal places, which is going to give me, so this is going to be 0.025 here. I need to look that up in the z table, and we're going to look for the z that corresponds to the value of 0.025. Well, here's our z table, and the way that z-scores work is as you go from and the way that these proportions work is as you go from the top left to the bottom right, and as you move in this direction, the values get progressively larger. So we're going to look for 0.02, and I'm just kind of scrolling my eyes, 0.02. I'm starting to get there. I'm seeing some 0.02s, and I'm looking for 0.025. 0.025. And sure enough, it is right there. 0.025. And now I need to ask myself, what is the Z value, or the Z that corresponds to the 2.5th percentile? Well, it's in this row. So it's negative 1.9, and it's in this column 6. Negative 1.96. And so I'm going to write in, I'm actually going to undo that question mark that I wrote. This line, the critical value corresponds to a Z-statistic of negative 1.96. On the other side, we need to look up the 97.5th percentile. So we're going to go to the other side of the distribution. We're going to start in the bottom left and move toward the top right. Again, they're getting progressively smaller now as we move bottom right to top left. And we're looking for 0.975. And I see it right here. And sure enough, it's the exact same value, just on the other side. It's 1.96. So we worked from proportion to Z-score. And so the Z-statistic on this side, that would be the critical value for Z, is equal to 1.96. So what we have determined is that if my Z is greater than 1.96, I would reject the null hypothesis, or if my Z is less than negative 1.96, I would reject my null hypothesis. Anything in between those values in here, we would not reject the null hypothesis because we do not yet have evidence against the null. So now let's go ahead and calculate this. So I know that Z is equal to X bar, which is my sample month, my new month, which is an average between my sales folks of 1120000, minus 1000000, which is the population mean. And I'm going to divide that by the standard deviation divided by the square root of n. The square root of n is 30, so it's the square root of 30 because I have 30 employees. And by the way, this little formula down here, this 100,000 divided by the standard deviation divided by the square root of n, this is what is called standard error. And you'll use this calculation in a number of test statistics. So we'll go ahead and calculate that out on your own. And once you calculate this out on your own, I want you to use that to draw a conclusion here. Did this new sales tactic significantly improve sales? So again, I start to solve this. I do Z is equal to 1,120,000 minus 1 million. So we end up with 120,000 on the top, or the numerator, divided by 100,000 divided by, and I went ahead and calculated this, the square root of 30 is equal to 5.48. So we go ahead and calculate the rest of this out. So 100,000 divided by 5.48 is equal to, so Z would then be equal to 120,000 divided by 18,248.18. And then we go ahead and solve that last little bit. So 120,000 divided by 18,248.18 is equal to, Z is equal to 6.58. Z is equal to 6.58. So now the question is, did my sales tactic significantly improve sales compared to the population average. We're going to look at the Z here. We're going to compare that to our critical values. Well, our Z fell somewhere way over here. So is there a significant effect? Yes. We would say that there is a significant effect, and this Z-score, remember, I wrote on my hands, test statistic, p-value, right? We wrote on our hands. I encourage you to do this. As the test statistic gets more extreme, the p-value decreases. 6.58 is quite far away from 0 in terms of a Z-statistic. And what happened was, once we got past that critical value, once we got past the critical value here of 1.96, we know that all p-values on this side of the critical value will be associated with a p-value of less than 0.05, which would lead us to say, sure enough, this is significant. So that's how we interpret and run a Z-statistic. Congratulations, you have just hand calculated your first test statistic, and you now know how to draw conclusions from it. And what we would say is that we have evidence against the null hypothesis, and this is more in favor of our research hypothesis, and this is what would lead us to say that yes, we reject the null hypothesis in favor of the alternative.